folks, so welcome to the video lecture, which is going to be our alternative to in-class lectures until we're somehow allowed to see each other again. Hopefully the quality is going to be okay. I've made a couple of tests and I think it's going to be all right. So yeah, let's just get started and see how it's going. So we started set theory last week at long last. We saw the axiom of non-vacuity that was saying that there must be at least one set, right? We've got to be having at least one of those sets in our universe of discourse, otherwise that wouldn't be much of a set theory. Then we introduced a second axiom, which is called the axiom of extensionality, which tells us that two sets A and B are identical with each other or equal if and only if they have exactly the same members. Thirdly, we looked at the relation of subset and we distinguished two kinds. The standard subset relation, which is the subset or equal relation. And then we also talked about the proper subset relation, and you had a little assignment question about that. And finally, we introduced the axiom of separation, which is a way of creating a set using a property. So the first thing we looked at was the principle of comprehension, which was telling us basically, hey, give me a property phi, and I can give you a new set of objects, which is the set of objects that have that property phi. But now we saw that this so-called principle couldn't be accepted as an axiom in set theory because it was leading to self-contradiction, and we looked at Russell's paradox as being a great example of how we could obtain such a contradiction. So what we did instead is adopt this axiom of separation, which is built on the same idea, but it's a little bit more restrictive, right? So here I'm not just giving you a property and you give me a set. I have to give you a set and a property, and what we get as a result is a new set. Maybe we'll call it B. And the idea is just this, right? Suppose I'm starting with a set A, and in addition to that, I have the property phi. The property phi is going to split my universe of discourse in two. On the one side, I'm going to have the things that have the property phi, and on the other hand, I'm going to have those that do not have the property phi. So here, I'm going to have that part of the set A, which is the thing that we are going to call B, the set B. Right? So the name axiom of separation is natural. It takes a set A and separates it in two using the property phi. Okay. Now, the way that notation works for the axiom of separation is as follows. So to say that A is in B is to say two things, right? From that, we can infer that A is in the set A, and that A has the property phi. Because if A is in B, it must meet the membership condition phi x, and moreover, it must be in A because B is the result of separating A in two. All right? And that works both ways, right? If I know that A is a member of A, and has the property phi, and if furthermore I know that B is defined that way, I can infer that A is a member of B. So this is how the axiom of separation works. We looked at that already. Now the question that I would like to ask at this point, because what we're going to do in this video is try to finish section 5.3 about separation and the pairing axiom. The first thing we're going to do is ask the question, well, what happens if we take the following property? We take the property maybe by definition, we say phi x is the property of not being identical to itself. So now we're going to consider that set which we obtained by separation. Separation of what, you may ask? Well, for all we've said so far, we have the axiom of non-vacuity that tells us that one set exists. We don't know what set, but at least one is going to exist, right? Axiom of extensionality doesn't tell us anything about whether sets exist or not. So all we know at this point is that there's at least one set, but we don't know which one. So call that set A, right? So what we're separating now is one of those sets, perhaps the only one, but at least one of those sets that is guaranteed to exist by the axiom of non-vacuity. Now, if there's one thing that we know at this point about the identity relation, is that, well, for all x, x is identical to itself, right? Identity is a reflexive relation. We saw that in the context of predicate logic, but also it was a consequence of the axiom of extensionality for sets. So all objects in set theory, whether they're element or sets, are identical to themselves. So that means that nothing satisfies this membership condition here, right? This one here is never satisfied. Oh, my red marker is not doing a great job. Fortunately, I came prepared. Got a big stack. We're going to be okay. But okay, so since that property is never satisfied for any object x, well, it's going to follow what? It's going to follow that set here that we know exists by virtue of the axiom of separation and the axiom of non-vacuity has to be empty, right? So this is an empty set. And we're going to introduce a special symbol for that. It's a 0 with a line on it. And this is the symbol that is going to be used to denote the empty set. Now, I say the empty set to suggest that there is only one empty set. Because how many members does the empty set have? Well, 0, right? If there was another set which is also empty, so empty set number 2, say, what elements would it have? Well, it would also have no elements whatsoever. So we see that those hypothetical 2 empty sets would have exactly the same members, namely none at all. So by extensionality, they have to be exactly the same. Okay? So the idea that we get from here is the following. For all x, x is not a member of the empty set. That follows directly from the fact that it's impossible to satisfy the membership condition of the empty set. Now, as we said, elements are something that they differ from sets, and the idea is that elements do not contain elements, as described by the membership relation. So the empty set and elements have this in common, that they don't have elements. But the empty set differs from all other elements in that it is a set, whereas the other ones aren't sets. Okay, so let's just do one example of what a theorem involving the empty set could be. Okay, so theorem for any set A, the empty set is a subset of A. Now that might sound a little bit funny. I hope you can still see. I know there's a bit of light here, but I cannot do anything about it. I tried to, shade the light, but there's nothing I can do, sadly. Okay, so the idea that the empty set is a subset of A makes sense, right? Because, well, that means that for all x, if x belongs to the empty set, then x belongs to A. Now, we know that this is always going to be false, which means that the conditional is going to be true. It's just like the example that you had in a previous assignment where you were asked to assess the truth value of the sentence. All European countries with a population larger than China have a population larger than 1 billion. Now, the antecedent here happens to be always false because there are no European countries with a population larger than China. So we had a situation where the antecedent is always false. We call those vacuously true. We don't need to know anything about the consequent in order to recognize the truth of such conditionals. Now let's just write it as a cleaner proof now that we have grasped the intuitive idea. So we can do that using a Fitch diagram, perhaps, right? So we want to get to this idea that the empty set is a subset of A. Now, in order to get there, we're going to want to show that for all x, if x is in the empty set, then x is in A. So let's take an arbitrary element, A, lowercase a. It's just like our normal Fitch diagram. And then we're going to do a conditional proof. So A is in the empty set, therefore A is in A. Now, as we saw, the consequent here doesn't really matter. We're going to get a contradiction anyway. Okay? So the way to get there is to just do a proof by contradiction. It's exactly the same as the case where you do the following deduction in propositional logic. So you have done that one before, just go back to it, and that's going to help you remember. If you want, you could just use that and tell me that you get the conclusion, but I'll just expand on it a little bit here, right? So from the fact that, so those are supposition. And now from line 1, well, I'm going to use the definition of the empty set, right? So A is in the set of X. Here there's something else, but I don't know. Let's use a name that we haven't used so far. It's just some set that is guaranteed to exist. I don't want to use the same name, not to have a problem. Right, so this is just the definition of the empty set following from line 1. Now, by the axiom of separation, the membership condition for the axiom of separation from line 3, it follows that A is not equal to A. However, we had a rule called identity introduction that we haven't really used so far because We never had a purpose for it. I just mentioned in passing that it was there. And it requires no line for its justification. Everything is identical to itself. And now, as you see, we have our contradiction here. That results from that. Now, the full argument is written in the notes as Theorem 5.7, so I'm not just going to rewrite that. Please go in the notes and look at Theorem 5.7, and you're going to get all the information you need. So there's going to be probably one more exercise in the homework assignment asking you to prove something about the empty set, but we're going to encounter this empty set many, many times in the future. Okay, so to this at this point, we have the axiom of vacuity that guarantees that at least one set exists. And then we have the axiom of separation that allows us to create subsets of those sets that exist by virtue of having some property. But now we'd like, but each of those sets, by the way, that are generated using the axiom of separations are smaller than the sets we already have. So now we'd like to start introducing a couple axioms. I will start with the first, that allows us to build bigger sets from sets that we already have. And that's very dangerous. We have to be careful when we do that, but the principles that we're going to use have been carefully vetted and are not going to lead us to contradiction. Okay? So the first one we're going to look at is the pairing axiom. So the pairing axiom says the following. For any two sets A and B, there is a set C such that A belongs to C and B belongs to C. Right? So C contains both A and B. It could also contain other junk, right? That's just an existential. There is a set that contains A and contains B, but we're not told whether or not C contains more junk or not, right? So based on that, what we're going to do is apply the principle, the axiom of separation. So now we're done with the axiom. What we're going to do is, well, take that set C, right? And we're going to look at the members of that set C. And we're going to want to say that, well, it contains A, right? So X is a member of C, but we want X to either be A or to be B. So we took that big set here, C, which is guaranteed to contain at least A and B. But by the membership condition, we also require that a member is either equal to A or that it is equal to B. So A and B are going to be the only members of that set that we have just created here. So we're going to introduce a special notation for that set. Curly brace, A, comma, B. That is the set that contains just A and B. And this is called an unordered pair. Why unordered? Because we could have written B comma A as well, and that would not have made a difference. Why? Because this junction is commutative, as we saw earlier. Okay? So now we have that new notation, and Earlier in the sort of informal preamble to set theory, we saw that we can describe sets by extension just by listing all of their elements, right? Basically, that way of describing sets is justified by the pairing axiom. Of course, if you want, you can write, triples, where here you have a set, I don't know, D. I should not have used C, perhaps. Anyway, such that X equals A, or X equals B, or X equals C. Well, just the normal thing. But for the exercises I'm going to give you, it's just going to be a set containing two objects, nothing more. So let me just introduce perhaps some Fitch-style rules that you will certainly want to use when you are constructing your proofs involving pairs of sets. So the first one is, well, if A, small a, is in the pair that contain the set A and B, it's going to follow that either A equals A, well, small a equals big A, or small a equals B. Right? That's just the membership condition for pairs from line N. Right? Easy breezy. Furthermore, you can just turn this around and now take this as your premise and obtain the conclusion that A is in the pair AB. All right? So that works both ways. Again, we're just going to write MC pair from line N. Easy, right? Now, there is a particular case of pairs, which is the case where the first and the second elements are the same. So that would be a set according to which, well, we have the members such that either X is A or X is A. Now, this is equivalent to just saying X is A. Right? So in order to take advantage of that and have a notation that is a little bit simpler, we're just going to write the following. Whoops. Such that X is A. Right? So that set here is called Singleton A. That is to say, it's a set containing a single element, which is A. So, of course, for something to be in that set, it has to be A, because A is the only member of that set. So let's introduce a couple Fitch rules to deal with sets like that. So, if A is in Singleton A, it follows that A equals A. That's just the membership condition for singletons. Not too bad. And once again, you can just reverse things. So if you know that A equals A, it follows that A is in singleton set A. Just like that. Nothing particularly crazy about that, I hope. So maybe we can just look at a couple examples of how that would be working. At this point, I should mention that if you read the notes of 5.3 last week, I had fewer examples. I've added a couple, so you might want to look at the updated version of the notes. So we're going to look at the following theorem. So that theorem tells us that the pair containing A and B equals singleton C if and only if A equals B equals C. And that means A equals B and B equals C and A equals C. Now, how would the proof go? How would the proof go? Well, let me do it as a Fitch diagram since it's our first case with the pairing axiom and singletons. So the first part of my proof, I'm going to go in that direction, so showing that this implies this. So I'm going to take as a premise that that set equals that set. And I'm going to try to get A equals B equals C. But let's proceed one at a time. Right? So suppose I first want to get A equals C. Because I know that's the easiest one, so that's why I'm starting with that. Now, you might look at this goal and think immediately, hey, maybe I'm going to use the property of anti-symmetry in order to try to get it, right? And that would be perfectly legitimate to try that. But when we're dealing with pairs and singletons, that normally is an incredibly cumbersome strategy. So instead, what we're going to try to do is, well, to get to the fact that A equals C, we're going to try to get it from, to get from the fact that A is in the singleton C set. And of course, if that's the case, then, well, there's only one member in that set. So A has to be equal to C, as the little Fitch rule told us, right? Now, we know that the set singleton C is identical with that one. So if we got this here, we would get this immediately by extensionality. Now, in order for A to be in that set, we need to know that either A is A or A is B. A has to be one of those two sets in order to be in that pair. But A equals A is something that we have already proved. We have already proved that identity is reflexive. So we can just introduce it right here. Right? So by reflexivity of identity, which has been proved before. Then line 3 is by disjunction introduction from line 2. 4 is what? It's the membership condition of pairs from line 3. And 5 is by extensionality from line 1 and 4. And finally, 6 is by the membership condition of singletons from line 5. All right, not so bad, I hope. Now, we've proved A equals C. We might also want to prove B equals C. Now, seriously, you just replace A here by B, right? Sorry, that's not a disjunction. That should be an equal sign. Sorry. Okay. Now you replace that A here by B, that A by B, that A by B, that A by B, and you get the conclusion that B equals C. So you're going to have A equals C, and you're going to have B equals C. Now, since set identity is symmetric, you can get C equals B. And since it is also transitive, you have A equals C, C equals B. Therefore, it follows that A equals B. And from that, you get A equals B equals C, because you know those three things are identical with each other. So we've done the first part of the proof, showing that if those two sets are equal, then A equals B equals C. The details, there are more details in the notes. Now, how do you go about doing that the other way around? Oops, doesn't matter. All right, so first we're going to suppose that A equals B equals C. And what we want to get to is the pair AB is equal to the singleton C, right? So we're going to want to do two things here. Now we're going to use our anti-symmetry. So we have two sub-goals. Oh, doesn't matter, by the way, if you write the little line underneath. Both are perfectly fine notation. So what we're going to want to do here is take an object and suppose that it's in the pair AB. Right? So that tells us that A is in A or A is in B. Now, since A equals C and B equals C, from this it follows that A is in C. You might want to do an argument using a proof by case here. In the notes I have done it, but if you wanted to just go from that to that in a proof in prose, telling me that you do that because A equals C and B equals C, that would be okay as well. So it follows from that. Sorry, I made a little mistake here. My bad. Why did I write membership when it's obviously identity? All right. So it follows from that A is in the set singleton C, because it happens to be exactly C. And the same argument about is going to work here. So the argument is really not too hard. So those two things together prove the theorem that the pair containing A and B is equal to that other set, singleton C, if and only if A and B and C are the same set. That's easy. In the note, there's another example, which is simpler than that one, so I'm not going to do it in addition to it, but all the details are given. That's one of the things that I have added since last week's version. So that one shows, maybe I'll do it. A is in B if and only if singleton A is a subset of B. That's a theorem. So all right, let's try to do it. And this time I'll do it as a Fitch diagram, so you don't have exactly the same as what's in the notes. So, well, first we're going to want to assume that A is in B. And our goal is to get that singleton A is a subset of B, right? Now, in order to do that, we're going to have a subproof that suppose that some arbitrary object is in A, and we're going to try to get to the conclusion that this arbitrary object is in B. Now, notice I skipped the universal introduction and things like that because it should be routine at this point, so I skip it, but but you're welcome, of course, to write it explicitly. So let's start from our supposition here for a conditional proof. Well, from the fact that A is in singleton A, it follows that A equals B, right? That's from the membership condition of singletons. Now, can we possibly use a substitution of identicals? Yes, we can, right? A is equal to B. What did I write there? I'm so sorry. Whew. A is equal to capital A. And that's what follows. I'm sorry about that. And now we use the substitution of identical. A equals A. And A shows up here, so it follows that A is in B by SI from line 1 and 3. Oh, but that's the subgoal we wanted to have, right? So now we can erase this and get directly to the conclusion. Maybe I can write, I don't know, CP plus universal introduction, to skip ahead a little bit. All right, so that shows that this implies this. Let's try to see how it would go the other way around. Right? Now, this is just a simple atomic sentence about A being a member of B. And here we have a universal sentence. Maybe it's worth writing it fully this time, just to see what we might have to do. Now notice that if we were to instantiate that universal conditional with a letter for which we would know independently that the antecedent is true, then we could just do a modus ponens and maybe get to the conclusion. So what I mean is that we might want to see what happens if we instantiate this sentence with the letter A. Why am I using the letter A? Because I would like to establish a connection between my goal and the consequence of that conditional. It's just like in those proofs we're doing with properties of relation. So now if I somehow have the antecedent, I will just do a modus ponens. But of course, A equals A by reflexivity of identity. And by the membership condition of singletons, it follows that A is a member of singleton A. Right? That's MC singleton from line 1, 2, 3, 4. And now I'm set up to do a modus ponens to get my conclusion. All right? So that's going to be all for that video. I'll take a little break, and then I'll come back, and we're going to talk about unions and the next section. All right? Cheers.